quantum sensing exploits unique quantum effects to measure quantities beyond the limits of classical physics. It promises to revolutionize the way we see and interact with the world around us. It will allow us to measure time, chemical changes, temperature, electric and magnetic fields with unprecedented precision and at miniscule scales, where everything is billions of meters small. Now scientists have developed a novel, non-invasive technique that uses quantum light to measure temperature at the nanoscale with high sensitivity. The method finds application both in fundamental research and in industry, from accurately measuring the temperature changes inside a cell to monitoring in real time the temperature of high-power nano-electronic components. To measure the temperature at such a small nanometric scale, the team of researchers uses diamond nanoparticles. These are extremely small particles up to 10,000 times smaller than the width of a human hair that fluoresce when illuminated with a laser. Pure diamond is transparent, but it can host inclusions of foreign atoms. Beyond giving diamond different colors, yellow, pink, blue, etc., these imperfections can emit light at specific wavelengths or colors when illuminated with a laser beam. The researchers found that there is a special regime, referred to as anti-Stokes, in which the intensity of the light emitted by these diamond color impurities depends strongly on temperature. Conventionally, a high-energy laser is used to excite these fluorescent impurities, which then give out lower energy photons of light. The excess of energy is lost as thermal vibrations or phonons in the crystal. In this anti-Stokes regime, the opposite occurs. The fluorescent color centers are illuminated with low energy light and can be excited only if they absorb the missing energy from the thermal vibrations or phonons from the surrounding environment. It turns out that the number of the available vibronic phonons varies exponentially with the temperature of the system. The higher the temperature, the exponentially higher is the number of available phonons and thus the resulting fluorescence given out by these atom-like impurities. This means that we can measure the temperature of a nanoscale object simply by looking at the fluorescence intensity emitted by these sensing nanoparticles in contact with it. Because the fluorescent diamond nanoparticles can be as small as just a few nanometers, they can be used as tiny nano-thermometers. This technique is all optical. The measurement only requires placing the nanoparticles in contact with the sample, and then measuring their optical fluorescence. Similar all-optical approaches to measure temperature using nanoparticles had already been proposed, but none can currently achieve both the sensitivity and the spatial resolution of this new technique based on anti-Stokes excitation. This is because in this regime, the intensity to temperature dependence is exponential in nature, and the sensing element is practically as small as a single atom in a few nanometer nanoparticle. This demonstration is not just a proof of concept realization. The method is immediately deployable. The researchers who developed it are currently using it for measuring temperature variations both in biological samples and in high-power electronic circuits.